So far, if you recall, we had discussed various ways of designing logic circuits using conventional gates like AND, OR, NOT, NAND, NOR, XOR, and also some functional blocks like multiplexer, decoders, etc. Now, in this lecture, we shall be looking at a slightly different way of designing logic functions, not using the conventional gates, but using something which is a little unconventional. The title of our talk here is lecture is threshold logic and threshold gates. So, in this lecture we shall be talking about something called threshold logic circuits and how we can implement threshold logic circuits using threshold gates. So, let us see the basic idea behind this so called threshold logic. Okay, the first thing is that in threshold logic, the basic element that we talk about is called a threshold element or a threshold gate. This is how a threshold gate looks like in its schematic form. So, you see in a threshold gate what are the basic components. If I show it as a rectangular box, there are some inputs which are applied. So, in this example I have shown that there are n inputs x 1, x 2 up to x n, and there is one output y. Now, there are a few other parameters you can see. Each input is assigned some weight. This W 1, W 2, W n, these are called weights. Okay. And there is another parameter called T. T is called a threshold. So, unlike a gate which we have learnt earlier AND, OR, NOT, etc., where only inputs and the output matters, here in addition you have some weights and threshold. Now, how does the weights and threshold play a role? You see this threshold element or threshold gate, the way it works, well, the inputs x 1 to x n, these are binary inputs, means they can be 0 or 1. The output y, this is also a binary output, but these weights w I and the threshold, these are not binary numbers, these are real numbers. Real number means they can be integers, they can be fractions, they can be negative also. They can be any arbitrary numbers, like for example, these weights and threshold values can be 1, they can be 2, they can be minus 3, 0.5, minus 2.5, etc. So, you can have any such numbers, integer numbers, not only integers, also numbers with fractional points, both positive and negative. Now, the way the output gets decided is as follows. The output y will be equal to 1 if the weighted sum of the inputs, by weighted sum we mean summation w I x I equal to 1 to n. So, you see here we have written down in the expanded form w 1 x 1, w 2 x 2 up to w n x n. If this weighted sum is greater than or equal to the threshold t, then the output will be 1, otherwise the output will be 0. This is how a basic threshold gate works. So, you have the inputs, you have the weights assigned to the inputs, you have a threshold. You compute the weighted sum. If the weighted sum is greater than or equal to the threshold, the output will be 1. If it is less than the threshold, the output will be 0. This is the functional behavior of a threshold gate. Okay. Now, let us try to understand why threshold logic and threshold gates are considered important today. The first thing is that threshold logic has a direct connection with neuromorphic computing. Well, neuromorphic computing is a branch of, you can say, computer science, where we are trying to mimic the behavior of a brain. The way the brain works, there are basic building blocks in the brain which are called neurons. Neurons work in a way which is very similar to threshold gate. There are weights, there is a concept of a weighted sum, there is a concept of a threshold. This is how people normally model a neuron. So, if you have a way to build a threshold gate, then using threshold gates you can possibly model the brain also. This is called neuromorphic computing. So, you can model the neurons that are present in the brains. Well, if you forget neuromorphic computing, even in conventional logic design, this can be considered as an interesting alternative, because we shall see a few examples that you can get much simpler circuit realizations for many functions, not all functions of course. For many functions, using threshold gates you can get very small circuits, very easy to design and implement. Okay. This can be one advantage, and second thing is that although threshold logic is relatively old, this is not a new concept, but technologies for implementing them efficiently is available only recently. Earlier the technology was not available, that is why people did not build circuits using threshold gates, but today people are thinking about building. For example, we talked about memristors earlier. Using memristors, people are working very actively towards building such threshold logic gates and with applications in neuromorphic computing. Okay? Fine. Let us take an example. Here we consider a 4 variable function. Let us look from the other side. Let us say that we want to implement a function like this. So, it is a sum of product specification where the true min terms are 1, 2, 3, 6 and 7. So, if you do a minimization using K map or any other method, you will see that your minimum form is this x 1 bar x 3 or x 2. Now, here I am not telling how, but this is a threshold logic implementation of this function. Now, you look at one thing, if you wanted to implement this function using conventional gates, then you would require an AND gate, with x 1 you would require a NOT gate, x 1 bar x 3, and this will go to an OR gate. You would be connecting x 2 here. So, you would be requiring 3 gates, but using threshold logic, this is just an example, using a single threshold element you can implement this function. Now, let us see how this single threshold element actually implements this function. You see here the weights that we have used are -1, 2 and +1, and the threshold is half. Let us see how this gate works. Look at this truth table. Well, on one side we have considered all possible input combinations of x 1, x 2, x 3, and because the weights are -1, 2 and 1, we are computing the weighted sum, as I had said, weight multiplied by the inputs. So, here the expression will be minus x 1 plus 2 x 2 plus x 3, which is this. So, with respect to the values of x 1, x 2 and x 3, if you calculate this expression, the values that you get are like this 0, 1, 2, 3, -1, 0, 1, 2. You can check. For example, for 0, 1, 1, it will be 0 plus 2 into 1 plus 1, which is 3, -1, 1, 0, 0, -1 plus 0 plus 0, -1. So, now you see, because the threshold is 0.5, half. So, among these how many of them are greater than equal to half and how many of them are less than half? You see this is greater than half, this is greater than half 2, 3 is also greater than half, 1 is also greater than half, 2 is also greater than half, but this one 0, -1 and 0, these are not greater than half, that is why you are getting the output 0. So, you can verify this is nothing but what you wanted to implement 1, 2, 3, 6, 7, you see this is this 1 corresponds to 0, 0, 1, which is 1, this is 1, 2, 0, 1, 0, this is 2, 1, 0, 1, 1, this is 3, 1, 1, 0 is 6 and 1, 1, 1 is 7. You see 1, 2, 3, 6, 7, this is what you wanted to implement. Okay. So, this example shows that how using a single threshold element or gate we can implement a complex switching function or switching expression. The next thing that we want to talk about is, well, we talked about functional completeness earlier. We said that when you build circuits, we should be confident that the basic building blocks that are given to us, those can be used to design and implement any circuit we want. For instance, AND or NOT, by definition they are functionally complete. So, if you have these three kind of gates given to us, we can design any circuit. Similarly, we proved NAND is functionally complete, NOR is functionally complete. So, if you give us only NAND gates, we can design any circuit using only NAND gates. Now, here we try to show that this threshold gate is also a functionally complete gate. So, using threshold gate alone, therefore, we can design any function we want. Let us see what is our logic. So, we are trying to say that threshold gate is functionally complete. The first thing is that this already we have seen through the example that we showed just now. Threshold gate is some kind of a generalization of conventional gates. They are more powerful because we can implement functions which otherwise would be requiring several conventional gates. We can implement the same function using a single threshold element or a single threshold gate. In that way, a threshold gate is more powerful because it can realize a larger class of functions. Now, the point we want to show here is that because we are saying functionally complete, we want to show that any conventional gate should be realized with a threshold gate. So, if we can show this, then we can prove that threshold gates are functionally complete. Now, the way we give the proof is through an example. We show a threshold gate implementation with the input weights -1 and -1 and the threshold of -1.5, -1.5. So, you can verify that this threshold gate actually implements the NAND function, and because NAND is functionally complete. So, if we can show that this threshold gate actually implements NAND, so we have proved that threshold gate is functionally complete. Now, let us see how this implements NAND. Let us quickly again draw the truth table here. So, x 1 and x 2 are the inputs. So, there can be 4 combinations 0 0, 0 1, 1 0 and 1 1. And here what is the weighted sum? -1 -1, so it will be minus x 1 minus x 2. So, the weighted sum is minus x 1 minus x 2. So, if you just calculate the weighted sum on these, it will be 0, -1, -1 and -2. So, what will be the output y? The threshold here, the threshold is -1.5. So, if this weighted sum is greater than or equal to t, then the output will be 1. So, in this case you see -1.5, the first 3 they are greater than -1.5, -2 is less than -1.5. So, for the first 3 the output will be 1, this the output will be 0. This is nothing but the NAND function, right. So, we have proved that using threshold gate we can construct a NAND gate and therefore, it is functionally complete. Okay. Now, the next question we ask is, can we implement any arbitrary function using a single threshold gate? Well, earlier we have seen that we had implemented a slightly complex function, say x 1 bar x 3 plus x 2, that kind of a function using a single gate. Now, the question is, given any arbitrary function, can we implement it using a single threshold gate? Let us try to answer this question. Of course, the answer is no, all functions cannot be implemented. Now, how do we prove this? We give a counter example. We show an example logic function and we give a justification why this cannot be implemented using threshold logic. Let us see. So, the first thing is that the answer is no, as I said. So, you cannot implement any function, arbitrary function using threshold gate. Now, the example we take is like this. Now, one thing we would like to just tell you, you just understand how a threshold gate works once more. The inputs are x 1, x 2, x 3 and x 4 with the weights W 1, W 2, W 3 and W 4. Now, when you calculate the weighted sum, right. Now, if and some particular input, let us say x 1 is 0, then that component x 1 W 1 will not appear in the weighted sum, this will become 0. So, you will have to consider only those combinations for which it is 1, only those terms will come. For example, if x 1 is 1 and x 3 is 1, then the weighted sum will be only x 1 W 1 plus x 3 W 3. X 2 and x 4 will not appear here because they are 0, right. Okay. So, with this example, because the two product terms here are x 1 x 2 and x 3 x 4. So, the output must be 1 for these two min terms. So, x 1 x 2, say x 1 x 2 must be 1, okay, must be 1, but x 3 x 4 can be anything, they can be 1, x 3 x 4 are actually do not care, then the first product term will be 1. But because we are talking about threshold gate, we are talking about the minimum. What is the minimum weighted sum? Minimum weighted sum will happen if these two are 0 0. So, let us take that 0 0 part x 3 bar x 4 bar. Similarly, for x 3 x 4 we take x 1 bar x 2 bar. Let us take these two min terms. So, if we take these two min terms, the output is supposed to be 1. So, what does this mean? Just in terms of the weighted sum, it will be x 1 W 1 plus x 2 W 2, because these two are 0, they will not come, and because x 1 x 2 are 1 and 1, it will be only W 1 plus W 2. Now, in order the output to be 1, this must be greater than or equal to the threshold. Similarly, for the second min term, x 3 x 4 are 1 1. So, W 3 plus W 4 must be greater than or equal to t, because your condition was W 3 x 3 plus W 4 x 4 greater than or equal to t. Now, x 3 and x 4 are 1 1. So, it is W 3 plus W 4 greater than or equal to t. So, if you add these two up, you get W 1 W 2 W 3 W 4, their sum is greater than or equal to twice t, right. Now, let us look at the false min terms. The output will be 0 for which min term? Now, the reverse. You see, output will be 1 if either x 1 x 2 is 1 or x 3 x 4 is 1. Now, output will be 0 if one of x 1 x 2 and one of x 3 x 4 are 0. So, let us look at two conditions here. Here x 1 is 0 and x 3 is 0, here x 2 is 0 and x 4 is 0. Just let us take this two. So, others also you can take and you can make a similar justification. So, if you take this, then you can arrive at conditions like this, because for this case your output is supposed to be 0. So, the weighted sum must be less than the threshold. For this case, because x 2 and x 4 are 1, so W 2 plus W 4 must be less than t, and for the second case x 1 and x 3, W 1 plus W 3 must be less than t. So, if you add them up, you see their sum is less than twice t. So, you see you have arrived at a contradiction. So, in one side you are saying that the sum of the weights must be greater than or equal to 2 t, on the other side you are saying it must be less than 2 t. So, the overall conclusion is we cannot find the value of weights W 1, W 2, W 3, W 4 such that these conditions are satisfied simultaneously. So, we can say that this function cannot be implemented using a single threshold gate. So, we have actually showed this as a counter example. Because we have a counter example, so this condition is not true. Okay? Fine. Let us take another example where we are showing a function that requires more than one threshold gates for implementation. So, here I am just showing the final solution, not going through the steps. This is a function of 6 variables. So, the lines are faint, I am actually showing the gates. In using conventional logic, you will be requiring 4 gates to implement, 2 AND gates and 2 OR gates. Now, what we are showing here is that using threshold logic gates, you can have 2 threshold logic gates to implement the same function. So, you can actually verify that it works. So, I leave it an exercise for you. For the first gate, the inputs you are applying are x 1, x 2 and x 3. These inputs are x 1, x 2 and x 3. The weights are 1, 1 and 2 and the threshold is 2. For the second gate, the inputs are x 4, x 5, the output of this gate is also an input, and x 6, and the weights are 1, 1, 1 and 3 and the threshold is 3. So, the function f that you get will correspond to this function, this you can verify. So, this is one function which can be implemented using 2 threshold gate, and this is an example realization of that, right. This you can check. So, the basic design problem in threshold gate is, given any arbitrary switching function, let us say of n variables, the main question we want to answer is to determine whether it can be realized by a single threshold gate, by a single threshold element, and if it is possible, what should be the weights, what should be the threshold value. So, the design problem of a threshold element or a threshold gate is to determine or find out what will be the value of my weights, what will be the value of the threshold. So, once we have to do this, your synthesis problem is solved. Okay. So, if a function can be implemented using a single threshold element, we say that it is a threshold function. So, a threshold function is a function which can be implemented by a single threshold gate, okay, like this. So, we shall take an example to show how we can systematically check for this and how we can determine the weights. So, we construct the truth table, and from every row of the truth table we obtain some inequality constraints. We shall see how. So, we will be having 2 to the power n such constraints, because there are 2 to the power n rows in the truth table. So, we will have to solve those 2 to the power n inequalities at the end. This is the basic idea. Let us take an example to work this out. We consider this function, and for this function we have constructed the truth table. So, we are showing the inputs x 1, x 2, x 3, the output f, and also the decimal equivalent of the inputs 0, 1, 2, 3, 4, 5, 6, 7. Now, suppose I am assuming that I can build a threshold gate to implement this function. So, the inputs will be x 1, x 2 and x 3. My weights will be W 1, W 2 and W 3. There will be a threshold T and the output will be f. So, if I have input 0, 0, 0, so my weighted sum will be 0, because the output is 1, that weighted sum must be greater than or equal to T. Similarly, for 0, 0, 1, the weighted sum will be x 3, W 3, only W 3, this is 1. So, W 3 also must be greater than or equal to T. For the row number 2, 0, 1, 0, so only x 2 is 1. So, W 2 it is 0. So, W 2 must be less than T, that is why it is 0. Here both x 2 and x 3 are 1. So, W 2 plus W 3, this is 1, should be greater than or equal to T. Here W 1 0 less than equal to T, W 1 plus W 3 0 less than equal to T, W 1 plus W 2 0 again less than T, and all 1 it is 0. So, the sum also should be less than T. So, you see we have got 8 inequality constraints directly from the truth table. From here we have to solve for W 1, W 2, W 3. Well, there are ways of solution. I am showing you just intuitively how you can go about doing it. D equal to 0, if you consider the first row, it says T should be negative. So, the first conclusion is T must be negative. Look at row 2, D equal to 2, it says W T is less than T, because T is negative. So, W T also must be negative and should be less than T. Similarly, row number 4 says W 1 less than T, because T is negative, W 1 should also be negative. So, this here you can see directly. And from rows 3 and 5, what you can see, it says W 2 plus W 3 is greater than equal to T, and W 1 plus W 3 is greater than equal to T. So, W 3 cancels out less than T, it says W T greater than equal to T and W 1 less than T. So, from there you can deduce W 2 greater than W 1, well, understanding that W 1, W 2 and T are all negative. And lastly, from D equal to 1 row, W 3 is greater than equal to T, this is another condition. So, combining this, you have these conditions to be satisfied, that W 3 should be greater than or equal to T, T must be, okay, you have these conditions, T must be greater than W 2 greater than W 1, because these conditions are there, T must be greater than W 2, T must be greater than W 1, and already you have shown W 2 must be greater than W 1. So, you can have any arbitrary choice that satisfies this, and of course, T must be negative. So, one possible choice I am showing here, there are infinite possible solutions. So, one solution is W 1 is minus 2, W 2 is minus 1, W 3 is plus 1 and T is minus 0.5. You see all these conditions are satisfied, W 3 greater than equal to T, T greater than equal to W 2, W 2 greater than equal to W 1. Okay. So, this is how, given a function, given a truth table, well, if it is a threshold function, you can deduce the values of the weights and the threshold. Okay. Now, we shall look at a couple of properties of threshold gates or threshold functions. The first property says that any threshold gate, as you know, it is characterized by the weights of the inputs and also the threshold. They taken together is called weight threshold vector. So, any threshold gate is characterized by its weight threshold vector. So, consider a function f which can be realized by a weight threshold vector W 1, W 2, W n and t, let us call it V 1. Let us say if we have any particular variable x j, the corresponding weight is W j. So, if we complement x j, so instead of x j in the function we make x j bar, then the corresponding function can be implemented only by negating the weight of that W j and changing the threshold from t to t minus W j. This can be proved. Okay. So, given a function, if you want to realize another function where one of the inputs are complemented, then you can just adjust the weights like this. This is one result I wanted to show, and another result is, let us consider this f is a threshold function and this is the corresponding weight threshold vector. Now, suppose we want to implement the complement of f. It says the complement function can be directly realized using the weight threshold vector, where you negate all the weights and the thresholds minus W 1, minus W 2, minus W n and minus t. Well, it is very easy to prove this, because you see from the first condition from V 1, because there is a threshold gate, the weighted sum of W n x I must be greater than or equal to t whenever f is 1, and it should be less than t whenever f is 0. Now, if you multiply both sides of this inequalities by minus 1, so this W I x I will become minus W I x I, t will become minus t, and this greater than will become less than will become greater than, right. So, from here you can see that if you make the weights and threshold negative and this minus less than greater than gets reversed. So, in the earlier case f was 1, now it is becoming 0. In the earlier case it was 0, now it is becoming 1. So, it is actually the complement function, right. So, we have seen a few such properties. There are many such properties of threshold functions. So, we are not going to go into the detail of that. If any of you are interested, there is some very nice literature available and books available on threshold logic functions. You can go through them, but I just wanted to give you a brief overview about threshold logic and threshold gates and how they can be used to implement switching functions. Thank you.